Okay, hello everyone. Well, we are jumping into the middle of a working session for, well, kind of for the physics project, except that this is the application of the physics project to metamathematics. And I think made great progress in kind of understanding how physics and metamathematics fit together. And what I'm trying to do here is look at some specific examples to get some nice sort of pedagogical examples of what's going on. And I really should rename this file actually, but okay. Now, first of all, Nick has written some. Let's see, two-way multi-replace has now been updated apparently, right?
Yeah,
Nick, why do you use general utilities? What function from general utilities do you use?
Well, a few. I don't know, condition, for example, because it's kind of annoying to write if something equals function, else identity. I don't write identity and something else.
We should add those things. Whatever you think you use from general utilities, you should enumerate those things, and we should make sure they get into the function repository. Anyway, okay. So let's take this from the top. We are looking at what we wanted to do, and I'm going to put this. Hold on. I'm going to move this file. That will be 22. Outline 01 becomes 22. Let me just do that.
Yeah.
That becomes Mathematics. It's 22 and gets moved over here. And then we are about to start Metamathematics 23. Okay, so what we want to do here, let's look back at 22. I'm going to summarize the pieces of 22. So what we want to do is we're looking at the way that derivations can happen in mathematics. So this is, we're going to start off with the basically, I don't know, x goes to y two-way rule, which is a little bit different from equals, but very similar to equals, is this. Okay, so now here, we want to, the first case of this is applying the axiom, well, okay, plus and associativity. We're going to also consider associativity later on. Oh, there was one thing I was thinking about, which is ways to generate variables other than co-substitution. I want to understand that when we get to that. Okay. Applying the axiom to expressions, making a multi-way graph. Okay, so now what we're going to do there is, this is pure substitution lemmas. And right, so this is, wait a minute, that includes both the substitution lemma, both the, okay, so here's the case. Okay, this was the case we thought was interesting, this one here. And actually we had layered digraph embedding of this. Okay, so Okay.
Great.
By the way, we should probably try and make this picture nicer by using, how can we make it so that it uses those blue boxes that come with multi-way systems? I mean, we could probably do this by saying, instead of all of this stuff, we can say multi-way function system, right?
What do you think, Nick?
No, I'm not sure about that because it requires a function.
And what do we think we have here? We have a function.
Well, yeah, but oh yeah, because it's not accumulating rules, then yeah.
Say that again? Yeah, right.
Because it's not accumulative. Yeah.
Hey, okay, great. Nice.
That looks nice.
Yeah.
Okay, so we're going to need that kind of format for some of these other things. That's just a minor issue.
Yeah. Okay.
Wait a minute. Oh, I see. In this case here, we didn't have, so we really need to now say graph there, layered digraph embedding. So that we start with the correct node, and then we probably need to say aspect ratio 1. Okay.
You also don't have to like write flattened values now. You can just list rules. Use list of rules now directly for the substitution memos.
Okay, so what do I do here? I just take this out?
Yeah, right. It wasn't doing anything here anyway. Well,
Okay,
values,
so
you still need values, but not list and flatten.
Mm-hmm.
If you want to add another rule, just use list of rules.
I see. Okay, I get it. Okay. So that's that case, right? And now within that, we now have this here. This is our proof. And well, that's a more complicated case. I mean, we'll have to clean up. Oops, that's not.
Well, yeah, the layered digraph embedding looks nicer.
Right. And we also need to clean up
the vertices, right?
Yeah. Okay, so now the proof, so to speak, I mean, to show this proof, so let's just understand the proof as you would generate it, where you say what part number to apply what to. In other words, if this was a find equational proof, how would we say what applies to? In other words, we at each stage we want to know the binding for the elements in the transformation.
Mm-hmm.
Nick, do we have a way to do that?
Yeah. Well, yeah. The output of substitution levels is an association. That's why you do values there. But keys contain all the information, what actually happened.
So how can we get that sequence there? How can we get that? Do you understand my question? I mean, how?
Well, you have to work with substitution levels somehow and record the keys.
By the way, this has note that there are multiple proofs of the same result. And so
there are two.
Aren't there more than two?
Well, between, oh yeah, no, I understand. Yeah.
Can go down that side as well.
Yeah, I see.
So, and we're probably going to want to show that somewhere else, because that's a relevant fact about these things, is that there are often multiple proofs. Okay, so now, okay, so Nick, is there any hope of doing this quickly, of getting that sequence?
Not sure, because you're dropping all the information. Well, you can use instead of nice graph, you can use two-way multi-graph list, right?
Okay.
And then just make it not accumulative, basically.
Okay,
using
fine.
row selection.
Okay, so then what I'm going to do there is code substitution is false.
Yeah, you have to make it not accumulative. And
How do I do
for
that?
You need like let me just send you the example. I had it somewhere.
Yeah, in the above case, I think there are actually six. There are 6 paths.
Okay.
6 possible paths. 2,
Yeah, okay, fine.
3. 4.
I mean, it's a cube. If I made that in 3D, it'll be just a simple cube.
Mm-hmm.
Okay, now, if I were to add in, okay, so let's add associativity here. And I might also want to try some different axiom system. I mean, let's start off with something that's mathematically recognizable, and then go to something that isn't.
Yes.
Okay, so including associativity, we will have let's just do the pure associativity case first. So that's this, and where instead of that we have the associative law. That's rather jolly. Okay. That it? Probably is. That's wild. Okay, but let's try. Okay, so this.
Yeah.
Let's try plus C there. Oh yeah, that's all it can
Yeah.
be.
Right.
Okay, so then plus C. I'm a little confused here. If I say A,
Okay.
and then I say this thing, plus A, I mean, I guess this is all that can happen. This is just distributing the brackets in different places.
Right.
And there's no way to get that to be more interesting. It's just a binomial-ish. It's just this is where the separator is. It's just making trees, basically. This is generating all possible trees, binary trees with 4 elements. All right?
We could show that.
Yeah, so wait. How do we generate? Okay, so this is vertex list of this is that. And so for each of those, we say expression tree. Is that right?
Oh, it's because it's multi-way function. Everything is a string there.
Oh, that's disgusting. That is such a stupid thing. We have got to fix this. Okay. So vertex list of, let's call it MW is that. Vertex list of MW. And then let's say to expression. We really need to get this fixed with the multi-way function stuff.
Yeah, I've made a note of it.
Okay, so then we're getting all these different
There you go.
possible trees. Okay, and and it doesn't, right, we can't reorder them. Okay, so now let's do commutativity and associativity. So there, Nick says we can just put them in a list, right?
Yeah.
Okay, so now, let's just do. This, okay, let's say I do A plus B plus C like this. And I do it for more steps. Oh. Okay. That may be obvious that it does that. Let's see what happens if I say A plus A plus A. That will be pretty degenerate, won't it? Yes.
Super. Yeah.
Okay, but if I do A plus B plus C plus D that we had before, and then I just say states graph structure. My gosh. Wow, that is a very complicated object. And I wonder if that's the whole thing.
Nick, do we need to apply canonicalization or unification or deduplication here at all?
No, we know we don't, because these are all distinct expressions.
Yeah. You don't want to do it here.
Yeah, I'm just making sure.
Okay, so if we take this,
it's because it's so large already.
Right, well, math is complicated, just like physics. Okay, so then if we say vertex list of this with the stupid two expression thing, and now we say on that expression tree with, what is it, vertex labels, tree element labels. What is the thing called? Tree element label arrow all arrow none. Is that right?
Yeah.
Wowee. Actually, what I really want to do is I want to not label the, do you know how to do that? To not label the intermediate nodes, but to label the things at the end.
You just want to label the leaves?
Yeah.
I'm not sure. I know how to change the data in the leaves, but not the label.
Okay. All right. Well, so these are all the equivalent expressions. Just for fun, to make it simpler, let's see what happens if we just do the AA case. I assume that that will then degenerate. Then it doesn't care about commutativity. Is that true or is that not true? So does that care about commutativity or not?
What do you mean by care?
Well, does it make any difference that there's commutativity in there?
No, maybe.
No, it doesn't. Okay. All right. Okay. All right. So this is the case. I don't really understand what this object is. I mean, we could have a more non-trivial proof here. And it may be that there are less proof paths from one thing to another. I'm not sure. Okay. All right, but then we're going to come back and look at other axiom systems later. Okay. So this is case one, where we're looking to expressions, right? Case two, actually, I'm going to promote this to case two is it applying the axiom to statements, right? So okay, so what does that look like? That is, by the way, I mean, just to do a non-trivial case of this, we could always do, oh, actually, wait a minute, I'm confused. There's an important simplification in these rules.
Which is?
That they don't generate variables.
Yeah.
Right? So this same idea, if I'm not mistaken, like if I was doing my axiom for Boolean algebra, you'd have to generate variables, wouldn't you?
Right.
Okay, so there's another case of this, which is applying to expressions, but generating variables. Now, why don't we have to do it in these cases?
What do you mean by we don't have to do it? Yeah.
Well, we can just take our original A, B, and so on, and just move those around. We don't have to do anything. We don't have to generate a new variable.
Sure.
Okay, so what's the minimal example of an axiom where we would have to generate a new variable? I think it's, if I'm not mistaken, it would just be something like X goes to, you know, Y, X, Y or something. Am I right?
Yeah, even simpler, just X, Y. You just have to have different number of variables.
Okay, well, so let's take a look at what that would look like. Okay, so in your case, right, we say X goes to, let's say, XY or YX, whatever, like that, right?
Mm-hmm.
So now we can just start it off from, well, whatever we want to start it off from A plus A or something, doesn't really matter.
Okay, yeah.
Okay, so now what's going on here?
Oh, because it's only one variable. If you want a different one each time, you have to like add that Uniquify option goes to true.
Okay, but this graph is wrong right now, correct? This graph is incorrect, right? Because it's got every instance of Y is the same here, right?
Yeah.
Okay, so
it depends how you look at it. In what
this result is wrong. Well, is correct if Y is a constant, right? So if we did that, for example, okay, I don't understand what that is at all.
No, because if you just have Y, it can only match Y. But if you have variable, it can match whatever.
Mm-hmm.
You want
Okay,
Y
but so this isn't
X.
a constant. But so wait a minute. There is a case. Is this result simply incorrect, or is this result what's happening here? When we generate a y, it's just a wrong result, isn't it? This is generating the same literal y blank every time, right? Which is going to give the wrong result in general. Am I right?
No, maybe that's what you want. It's like,
Well,
what
what
do
does
you
it
mean by
mean?
wrong result? You just have one variable in your system.
Okay, but then in mathematical terms, this will be a constant. That y blank would then be a constant, correct? Like pi or something. This is not representing that we will not be able to get all true statements that are generated by this thing will not be produced if we take y to be the same every time. I think that's correct.
Well, in
Because,
this sense,
yeah, right. So, okay, so not all. I mean, so in effect, y is treated as a constant here. Am I right?
Yeah, I
no,
understand
it's
the
not.
reasoning.
It's not a constant. It still can match any expression if you use it as a
I see.
substitution, right?
I see. Because it still matches, but all instances of y have to match the same thing.
Right. If like at some point there's going to be two y's.
Yeah.
In order
Right,
to go forward.
So let's find the case where there are two y's here. I think there are fairly many of those. Is this really the minimal case? X goes to y plus x. Is that actually the minimal case of where this problem will occur? Does it not occur with x goes to y?
Well, I was wondering about that.
You can just have a constant on one side, any constant, and a variable on another. Right? Then we can generate a variable.
Okay, so if you say, so what are you suggesting? You're suggesting A, two-way rule, X blank.
Yeah. And there is the two x's, for example.
Right. Which I don't quite understand why that doesn't go. It probably does keep going.
No, it's not. It can't expand anymore. It's just replacing variable with a constant.
And why on earth does the layered digraph embedding not bring the AA to the top?
Yeah.
Okay, but so this is okay. So that's the minimal case of that. Right. By the way, up here, those are all variables. Right, but that's a constant there. Okay, so now we need to do the case where this is uniquifying. Okay, so what do we do there? We have an option to substitution lemmas that says uniquify. Is that right? Unique.
Yes.
With a U now, right?
Yeah, it's with the U now.
Yeah, with the U now.
Correct spell.
Uniquify goes to true.
Okay, so let's go 3 steps here. I don't know why the layered digraph embedding isn't working with AA at the top. Is that obvious why that's not working?
Not to me.
Oh, how would it know that it's considered a root vertex?
Well, then let's just give it the root. How do we give it the root?
Well, maybe you can. Well, I'm not sure. I've never done that. Maybe just root and the name of the vertex.
Well, even in this case, it's already, I mean, we need to, okay. So we're going to, so now here, let's consider this case where it goes states graph structure. Let's go 5 steps or something. So there are many things that get left out in the cold here. Why is that? Because they are variables, because they are not variables that ever connect to anything, right? But I don't understand that. Why aren't they unifying? Do you understand what I'm asking?
Yes. Yes, I understand.
Well, there are different variables. If you want a canonicalization, you add canonicalization. Because here at each
I see.
new replacement, you have a new variable.
Yeah, let's see what the effect of canonicalization is.
So then we put in canonicalize here.
Right.
And then, wow.
Okay, so that now is the same as this, as it happens. But that shouldn't have an XX in it anymore.
Maybe it should X.
Oh, it doesn't. It has AB there.
Yeah. Different ones.
And conveniently, this we're going to have to talk about how the canonicalization works and what the actual names of the variables are there, because it's super confusing in this case. Because we've got both A and A blank.
Right. Yeah.
Okay. So this is one complication, is generating variables, right?
Yes.
And in general, let's see.
This is generating variables, but just with substitution, right?
Yeah.
Yeah.
But and what's the criterion for when you have to generate variables? Anytime you're not just rearranging structure, you have to generate variables.
Oh, it's simple. If you have a rule that on the right hand side has a variable that is not on the left hand side,
right,
then it's a new variable.
Right. Right, which is the same as generating atoms of space.
I see. So there are just certain rules that generate variables and certain ones that don't.
Right.
Yeah.
And in the case of the, in the physics project, we have not made much of a distinction here.
Right.
And nor will we here, I suspect. But in the actual implementation of mathematics, it's a big mess. When we get to combinators, it's not going to matter, I think. At this stage, it still matters. But when we're at the combinator level, it's not going to matter. Correct?
Well, sure. I mean,
what was this? Sorry, Nick, you'd sent through that rule selection function. What is that doing?
It makes a two-way multi-replace list, not accumulative, basically. It just picks the first rule. Always.
Oh, okay, fine. So that was what we needed for the proof up here, right?
Yeah.
Well, that's not very helpful. Why are those looking different from these?
Because
because it's not applied to ABCD. It's a self-applied rule.
Yeah.
Can we apply it to ABCD?
No. because
Okay. All right.
it's
Okay.
called two-way multi-replace.
Yeah. Okay. Okay. Okay.
So it's very specific. You can apply it to A, B, C, D, two-way rules, something. True, for example.
Oh, you mean we can put this in
Yeah.
as a two-way rule?
Yeah. With the right-hand side being some constant. Just true.
Say true. Yeah.
That's sure.
The suggestion is being made on live stream that we should look at propositional calculus. We could. I think these are even easier than propositional calculus. In fact, yeah, it's a lot easier because propositional calculus needs a model to be easy to understand. Can we make a note of? Let's come back to that when we go through and look at this in the models case. All right, let's keep going on our sequence here. Okay, so
yeah,
now,
I mean, by the way, you asked whether or not this will be different at the combinator level, and it will be. I mean, here we're looking at the entailments of axioms. It's just very different than whatever the evaluations are at the combinator level, right?
I don't think so. I don't think so. I think what happens in the combinator case, the only difference is there's no generation of variables, because in the combinator case, let me think about that for a second. You know what the issue is? No, there could be. The reason there isn't is because the actual SK combinator rules do not have more variables on the right-hand side than on the left-hand side. Boy, old Moses Schoenfinkel dodged a bullet there. Yeah, you see that could be yeah, right. I mean, that's exactly, and that's, by the way, a feature again of the Wolfram language design of patterns is you can't have more pattern variables on the right than you have on the left. They're just no longer, you see what I'm saying? That they're not uniquified. And that's why a two-way rule.
Yes.
A two-way rule has this issue. So, I mean, okay, so the basic point is a two-way rule will have the variables need to be generated issue. In a way that one-way rules will not. I.e., you know, we can say things like x blank, y blank goes to, you know, x plus y or something. We don't have to worry. And if we said x blank, y blank goes to x plus y plus z, it naturally, just by syntax, is not binding. There's no local binding of the z.
Right.
Oh boy, so many bullets dodged in these designs. I mean, in other words, that case. Yeah, I mean, so in that case, for the two-way rule, if this becomes a two-way rule, Nick, maybe you can comment on this. If this becomes a two-way rule, and those are all blanks, then we necessarily have to generate variables in the z blank case.
Yeah.
Correct?
Yeah.
Huh. Fascinating. Okay. Another unknown bullet dodged 40 years ago. Actually, SMP did it in a more bizarre way. SMP wasn't as obvious that bullet was being dodged. Okay, in any case. Okay, let's come back now to applying the axioms to statements. Okay, so a typical statement, I think we had some examples here. would be the statement AB goes to CD. Okay, so that here, that's a statement. I mean, another possible statement is, so a statement, typical statement, so this is applying axioms to statements where, so this is a code not equal to data situation. The axioms are the code.
The statements are
Statements of the data.
Yeah.
But now the code and data are basically in the same format, right? Which they weren't previously. So that could be a statement as well as A blank plus B blank. This could also be a statement, if I'm not mistaken, right, guys? Nick, that's true. With all the technology we have, that's also a possible statement.
Yeah, but it's almost an all-knowing statement. So
what is that basically like? A goes to B, a two-way rule B.
Everything plus everything is equal. Anything plus anything. You can do anything there.
I see. So this isn't very useful. This one isn't very useful. A not very useful statement. But we could have a less trivial statement. Okay, but here we're applying, okay, so let's go ahead and apply these rules to statements. So we could do exactly the same thing we did up here, wherever we were, this one here, right?
You can fix that rule selection really quick, by the way. Example.
I'm sorry, say that again?
That rule selection function thing.
You can fix this?
Yeah, just range 2. It requires range 2 because we're preserving 2 rules.
Okay, this is great. Let's come back to this in just a second. Let me just, because then we want to extract those proofs. Okay, so this is this, and now what we want to do is to apply it to this, which happens to have the form of a two-way rule. Oh, it's so grotesque with the we've got to fix this. But anyway, that's this thing applied not to the plus version, but to the two-way rule there. So fine, it's a syntactic thing that we can do, right? That transforms rules. We could also, okay, so now a subcase of this is self-applying to the original to the axiom.
Yes.
Okay, which is now possible. Okay, not very exciting, but it'll do that. Is that meaningful, or is that the way? Is that way because we didn't canonicalize? If we canonicalize, doesn't that? What should we in fact? We don't need to do Uniquify, but we do need to do canonicalize, don't we? Here.
Well, if you wanna basically remove all the two-way rules that kind of the same.
Yes, they're the same up to variable renaming. Yeah.
Right.
Under pattern renaming, pattern/variable renaming. Okay. So that's self-applying the axiom. Now, there are two different branches we can go on here. There's co-substitution.
Yes.
And there is, okay, we need co-substitution to reach find equational proof, don't we? Here, okay, I'm going to go back and get those proofs now.
Well, we've discussed this before. I think the prevailing conjecture has been that just using substitution would just take a very, very long time. That's
No, I understand
that's
that,
the most generous interpretation. It might not even work at all, but if it did, it would
well,
take a very long time.
I mean, we need to understand whether it will work.
Yeah.
Okay, whether there's something mathematically incomplete about just using substitution. Okay, so there's two directions. There's co-substitution and there's accumulative. Okay, so let's look at both of these cases for a minute. But first of all, let's derive these things here. So we're trying to derive A, B, C, D goes to, we're trying to derive that path there, right?
Yes.
Okay, so Nick, what do we need to do here? What are the nodes in this case are things of that form. So you're saying what we do is we take, it's taking 5 steps. Okay, it's let's reach a fixed point. Okay, so we take that and we say that, and we say find shortest path. Of that, and then this thing here, correct? Is that right?
Yeah, but you have to like have a two-way rules there. Like it should be true on the right or something.
What?
Well, because we have like in order to insert it into our system, we have to have a constant true.
Okay, this isn't what we want. This isn't what we want. It's not what we want. Okay, because this is, no, this is not what we want. This is a different case. Yeah, this is a different case. This is just going to totally confuse everything. No, what we want to do here is really a different case. You see why it's a different case? I mean, this is purely substituting into expressions, right?
Okay.
Yeah.
Okay, so what we want to know is, and we probably just look at this by hand, we want to know which replacement was actually done here to get to this.
Well, you can kind of do it there. I guess you don't like that it's the first rule being applied to itself also.
Yeah, well, right.
Well,
But
then
I mean,
you can like just tweak a rule selection function a little bit. So instead of tuples 2, you also delete the tuples 1, 1. Delete the pair 1, 1. You don't want 1, 1 there.
we just say delete in that tuples.
Cases. Yeah, delete cases 1, 1. So there's gonna be.
I don't believe in this. I don't think this is right. I think this is still a hack, and I don't think it's going to work correctly. No, I mean, this isn't right. We don't want this. We want single expressions, not these things. See what I'm saying?
Yeah, okay. Yeah, it's a hack. It's just, but it can be done.
Okay, but
more hacking.
With more hacking. Okay, but because what we're trying to do, we just need one example where we're seeing which things here. So in find equational proof, it would give a part number. And that's what you're doing as well, is give a part number for what the transformation is to get to here, correct?
Yeah, right. Because that's why it's easier with those graphs. They have it as a edge tags already. So we can extract easily this information.
Right, but I mean, this proof here, we can get this proof Okay, those are the terms, those are the sequence of things for the proof, right? So now to represent that proof, I mean, if we just put that in a column, we can represent that proof by essentially underlining the pieces that are being changed.
Yeah,
right?
I understand. Yeah.
And actually, more to the point, what we want to do is indicate that this is the X, that's the Y. So what we're going to want here is something where yeah, I mean, roughly the picture we're going to want is labeled CX, circle plus, labeled CY. That's rather ugly, but I mean, okay, let's say style of this, comma small. Maybe a different color. Okay, and then this is going to want to show that those two go into an event to get to something, and then it comes
I
out.
see. Yeah, I see where you're going with this. Okay.
Right?
Yeah.
So that we're indicating how the axioms get applied to generate the result.
Right.
Okay. So if you can make a note, that's one of the pictures that we're going to need. James, are you getting that, or should I put it in this file?
I just said, yeah, I'm writing it down. Yeah.
Okay. All right. Okay.
No,
Okay.
maybe you can try a quick hack to the rule selection, the last one.
Okay. Yep.
So to this, so change range 2 back to range 1 and append to the whole list pair 2, 2.
Doesn't look promising to me.
No, there's still some fluff in there, but it's mostly the same. Weird.
I don't know what that is. Anyway, okay. All right. Okay. So now here, okay, this is applying axioms to statements. All right, where were we going next? The next thing we were looking at.
You want to do co-substitution or accumulative?
No, I want to understand what would happen if we were generating variables here. Nothing much. I think we want to do a cumulative next.
Yeah, okay.
But I'm trying to understand at what point. Okay, hold on. Just so I understand. Okay, so let's do up here a non-trivial Boolean algebra example, or an example with some other let's see. So let's just do here Boolean algebra example. So now what we would do is we would take, oh, look at that. Is that you can apply that to axiomatic theory?
Yeah.
Okay, so there's my magnificent axiom, which I can never remember. My friend the computer knows it well, but I do not. Okay, so now what we have to ask ourselves is, from an expression point of view, there's an example in NKS. Well, I've given some axioms in NKS where, but okay, from an expression point of view, let's say we're trying to prove X blank, Y blank. So here we've got generation of variables. We need generation of variables here. So now let's say we're trying to prove that, our goal is to prove that this, center dot Y blank, we're trying to establish the result. We're trying to establish that result.
Okay.
I see. So we've got two ways to do that. One way to do it, when we say applying axioms to statements, we would be applying this action to that statement and trying to turn it into a tautology, right? Down here. You see what I'm saying?
Yeah, the tautology should be like in future entailment cone of both.
Okay, I need to understand that. Okay, so you're saying, I see what you're saying. Yeah, okay. Okay, so then, okay, so one way to do the proof here, which we probably are not going to be able to do, it's probably way too complicated a proof.
You can try find the equation of proof to see how complicated it is.
It's 100 steps. It's 100 steps according to find equational proof. But find equational proof. It could be like 10,000 steps if we're just using the axiom.
Alone.
Yeah. But maybe we need a simpler example of this.
Why don't we just use like commutative group theory? Simpler axiom.
Yeah, but what are we going to prove?
Some simple statement.
I had an example in NKS that wasn't too bad. Hold on one second. Let me find that. Okay, this is what I did in NKS. That's the analogous thing. So this is now using, that's a Boolean algebra example where that's a proof, but yeah, okay, all right. I think I understand. We'll come back and look at specific examples. Now, in this case here, to prove okay, so wait a minute. Applying the axioms to statements. Then we've got another subcase here. Oh, okay. So where we're purely self-applying, aka the gas of statements. In other words, if we're thinking of this as there's a certain gas of statements, and this is where I wanted to make that token event graph also.
Yes.
There's a gas of statements, and those statements, we start off with that gas of statements, which might just be a single statement, but and then we're asking, how do those statements, start with initial statements, then let them interact. Okay, so let's see those interactions now. So what we want is a token event graph. I think this is what we were about to do yesterday. Yesterday.
Now, wait, what do you mean by a gas of statements here? This is
I mean a whole collection of statements. We've been calling it an ocean before.
Yeah, okay.
I'm renaming it a gas. Because the statements... Go ahead.
We also called it what of statements.
VAT, a statement.
What?
Yeah.
VAT of statements. Yeah, but I'm calling it a gas of... What's that?
And also pool.
Pool. Yeah, pool is not a bad
Yeah,
word.
we've had different idealizations.
AKA.
So when they change, I just need to update myself, right?
Pool of statements, VAT of statements.
You see, the other distinction is, at least as I have remembered it, when we use the term ocean, and sometimes even VAT, we're actually speaking at the machine level, at the syntactic level, right? Because you also have this kind of, I just call it the machine ocean, right? You have this ocean of pre-semantic, potentially absurd, potentially useless or non-utilized statements at the machine code level. They might not even make it to metamathematical space level.
All right. Okay. So there's another level then, which is these are quotes actually generated statements.
Well, it's just a metamathematical gas. This gas resides in metamathematical space. That's the point, right?
I think so.
Yeah, and there are other kinds of water bodies or
living. Okay, so this is living in metamathematical space.
That's right.
But as opposed to statements which are syntactic, but which don't have any proof connection to anything else.
Yeah, are those even statements at that point at the combinator level?
Well, I don't know what statements are at the combinator level. At the combinator level, this is going to go even below.
Yeah.
Look, at the combinator level, at some point there has to be a law of inference, and that's what, or an entailment, and that's what we're doing substitution for that here. Yeah. In the case of combinators, it's some kind of function application thing.
Yes, but there's this critical question, which is there's some sort of interface where you have say some sort of halo in machine space, right? You have a few different combinators. We have examples of this where you have, say, multiple combinators for addition. Okay, so you have some sort of addition halo. Okay, the question is, what happens at the interface where you have some sort of, commonly generated, you have something that's commonly generated by combinators, and then that rises to metamathematical space because it is it's common, it's able to persist. And what Nick and I discussed last night is that there's something called definitional entailment. You basically have this kind of passage from something that's some sort of halo in combinator space or machine code space. So it actually gets named, it actually becomes some sort of a statement in this kind of gas, or it can become an axiom that can be subject to entailments.
Right. We're talking about, okay, so look, this is combinator / machine code level.
Yeah.
Okay, and you're saying, which we're not yet discussing because we've still got much more to do up here.
No, I only bring it up so that we're kind of sorting out the language and the terminology that we're using.
Okay, all right. So in this case, it's like, start from all possible combinator expressions.
Yeah.
Now we have a certain, with a certain sort of law of application, which is now fixed here, and which is analogous to our substitution rule, I think. Not sure. A certain law of application, and then, okay, so certain certain sort of collections of combinator expressions. There's a very biological aspect to this, because I think it's just like it's like proteins in the origin of life, right? We certain random collections of proteins turned out to make some autocatalytic set or something, and then they could be used for some purpose that turned into metabolism or something.
Yes. Yes.
Okay, so there's basically certain collections of combinatorial expressions can be identified as having a purpose, so to speak, as having a meaning / purpose.
Yes.
AKA,
yeah.
CF, recruitment of molecules for life.
Yeah. And I mean, in our lexicon, basically what we're saying is that machine halos can be subject to definitional entailment. And then they can they can be in the gaseous statements. Now, Nick has a more.
What is definitional entailment?
All right, Nick, you ready?
What? Well, I have one example.
I really like this. I really like this idea of definitional entailment that Nick has.
Okay, all right.
He kind of explained it to me last night.
Definitional entailment.
Really like it because I've been wondering how exactly the machine code metamath interface basically operates. I think it operates according to this, according to definitional entailment.
What the heck is this? Okay, hold on.
No, Nick,
what you've got,
Nick, it needs some narration. You're gonna have to describe what this is a little bit.
Okay, so this is a set of axioms, basically. Is that right?
No, it's not a set of axioms. So it's a rule that's kind of searching in your in your ocean or gas of statements. Those two rules that match these patterns, all of them simultaneous, and as soon as it finds it, it can make this entailment and name all of those actual combinators or whatever underneath somehow with an actual symbol.
So I see. So your point is, as soon as one finds a cluster of
halo or cloud or something,
right, a cluster of combinator expressions that match the LHS.
Yeah.
These can be we can now identify.
Yeah, they can be identified.
Can now identify the lumps of combinators with these names. However, with the specified names.
There's a nuanced caveat that has to be made here, though, which is this is kind of just speaking informally when you say we can now identify them, because that's not quite what it is. It's not saying necessarily that they become observable by us, by human observers, so to speak. I still understand it as basically meaning it passes from machine space to metamathematical space, which means someone could observe it, but it might not be us. You understand?
Sure. No, I understand that. But basically, how does one piggyback on the raw combinators to make a meaningful computation? A describable computation.
You mean like an entailment?
No. I mean, this is the same thing as what people try to do in quantum computing all the time. Oh, we've got this ion trap or something. We've got these configuration of ions. Let's use that to represent a 1 or something.
Well, the reason why I'm a little caught off guard is we haven't used this term computation, right? We haven't used this at all so far.
Used that here. We haven't used that here.
So what's a synonym for computation here? That's why I was asking about entailment. No. Right.
It's a fine. I mean, it's just something like this mathematical structure. I mean, it's something where we can. What you're saying is, whenever you it's like the comparison is, how do you make a switch out of pick a thing, out of magnetic bubbles? Okay. And the answer is you have to, this is a place where, or how do you make a Turing machine out of S combinators? There's a certain interpretation step.
And that's definitional entailment.
Yes, that's what I'm saying. Yeah, so AKA interpretation step. So in other words, what this is saying is, there is a raw computational process going on down at the combinator level effectively. And sometimes you can say, oh, I recognize that thing. You can think of it as plus.
Yeah.
And there may be many ways to do that. And that's just like, because okay, so let me think about what it means to say there are many ways to do it.
At the combinator level?
Yes,
Yeah.
because that's our model for
exactly.
So in general, there are many ways to make e.g. plus at the combinator level.
I mean, I understand it as meaning that it has syntactic density, right? It can arise in many ways syntactically, and that gives it some kind of oomph semantically on the other side.
Right. There are many ways to make plus. So the fact that there are many ways to do this, and they're decently dense in
machine space.
Syntactic space.
Yeah, they're machine dense. They're syntactically dense, right?
Makes this a quotes robust concept.
Yeah, that's the idea.
Okay, so now the question of the general laws of mathematics question is whether, given such a robust concept, whether it is shredded when you do things to it.
Yeah. Right.
And that's the criterion for whether the thing, I mean, that is the big claim we're making, is that the fundamental thing that makes human mathematics possible is that robust concepts don't get shredded by essentially proof entailments.
Right. And this is another delicate point. This is kind of another conjecture, I suppose, which is, on the one hand, there's this kind of filter from machine level to metamathematical level. And this has to do with syntactic density. See, I suspect, and actually, I don't think this is controversial, you can have something that is syntactically dense and it's robust enough to make its way into metamathematical space. But that doesn't mean that its own entailment cone in metamathematical space is observer friendly, right? So there's a couple of different ways in which you can have
yes, I understand. Robust concepts,
right?
There's still,
yeah. There's syntactic robustness, and then there's, like, I don't know, semantic or observer theoretical robustness, right? On the one hand, you have to be able to get from the combinator level to metamathematical space, but then even within metamathematical space, you have entailment cones that aren't observer friendly.
Okay, well, let's think about that for a second. So this level, this combinator level, is not something one usually thinks about in mathematics. This is below mathematics. This is basically below axiomatic mathematics.
This is releological mathematics, right?
Possibly, yes. But although releology is more, I mean, okay, this is below standard axiomatic mathematics.
Right.
In other words, that's the same statement that people have been making for 100 years. You could use combinators, but you don't want to.
Yeah, but now we kind of want to, right?
Well, but what we're doing here is combinators provide a uniform infrastructure for thinking about, what's going on.
Yeah.
Okay, so hold on. So first question is, do things raise above the combinator level to the point where they're robust enough that, where it's like, this is natural language design with a different parsing of the natural and the language. This is analogous to emergent language design, basically. i.e., if there's a common cluster of combinators, give it a name.
Yeah. I mean,
So
in some sense, I mean, it depends on how much you want to think about the Rule. In some sense, it's not as though it's being designed. It's like all the rules are there. You're basically, we have a kind of a filter structure for understanding how we get from this machine ocean, right? Understanding how more sophisticated creatures basically crawl out of the machine ocean and start being involved.
Well, right,
in
but I have a
mathematics.
feeling that in the end, the thing is a self-fulfilling story, in the sense that I think that the structure of observers up in the Ruliad
Yeah.
is going to actually determine what makes sense as emergent language design. In other words,
Sure.
I suspect that this syntactic density is going to depend on reference frame in some way. That would be my guess.
Yeah. Yeah.
Probably. Okay, so if that's the case, if syntactic density depends on reference frame, then probably the whole story of what you identify as being an emergent concept, so to speak, depends on that reference frame, which is also saying, I mean, with respect to the Ruliad, so you can think about this in terms of actual natural language as well. Like there's certain things that happen in the world. This is the same self-fulfilling story. Okay, there are things that happen in the world, and once you have once you start making tables, you need a name for table. Once you have that name, you make more tables.
Yep.
But
yep.
It's essentially the choice of reference frame. That is, there could be many things you could make out of wood or something, but our particular way of sampling what happens in the universe, it's self-fulfilling in that way.
But I want to make a kind of a more optimistic gesture, or it's kind of a question, which is, so in terms of syntactic density, at least, let's say, especially if you're doing computer experiments, right? You find that certain combinators have some sort of I don't know if you want to call it confluent behavior, but you have some impression that there's some sort of a halo or a cloud, and you have no idea what it corresponds to.
Sure.
Right? You have no idea. So, I mean, in some sense, you're saying that syntactic density depends on the reference frame, in the sense that maybe you see that there's some sort of a halo, but you really have no idea how to name it.
No,
right? But it's, you could still see that it's there, and it's still not clear to me what you would do in that kind of a situation.
Well, it's the same story as in machine learning. Machine learning, you can perfectly well see the neural net chooses certain features. We don't have names for those features. It's a free-floating alien intelligence, so to speak, that's finding these things. And yes, we can identify. I mean, this is the question, which I think in the end is again self-fulfilling. This is the question of, can you identify that there is an alien intelligence there, so to speak, that it is finding concepts, or is there no way? Is the very fact that you're identifying it a consequence of the way that you do the identification? Anyway, I think this is, let's come back to our concrete thing. I think this is very good. I mean, I think we're understanding now better. In a sense, what we're doing here is we're going both above, we're looking at the consequences of axioms, and we're looking at how you build up axioms from underneath.
Yes, and we have an idea, an understanding now of how those two interface with each other. Anyway, maybe.
Yes, I think we do, but I think okay, but we're going to have to come back to this question about what the analog of laws of inference is. Yeah. See, another thing about our friend the Ruliad is that it contains all possible laws of inference.
Well, yeah.
And the whole point is that in the end, it's not even going to matter. The emergent mathematical structure is in the end not going to care about the laws of inference. But we need to get to, we have only comparatively limited time, and I really want to get through some of this stuff and then get to the metamath
Yeah, sure.
empirical metamath stuff. Okay, so let's quickly
You want to
try
go
to
back
go
to a cumulative or
No, I want to go
simplifying?
back to purely self-applying gas of statements, and I want to make the token event graph. Nick, how do we make the token event graph here? I think we made one of these before.
Yeah, we made some. We just used token event graph function and substitution lemmas inside.
Okay, but so can we make a token event graph? Let's see. A token event graph of expressions isn't very interesting. It's really the token event graph of statements that we want to make, I believe. Okay, so let's make the token event graph for this thing here. How would we do that?
Or just go to the Twoway rule. That's going to be our initial condition for the token event graph.
Well, here it is, this one here. Okay, there it is. What would you like? There. So this becomes token event graph, right?
Right.
And then what?
And I think it
We
has
have
to
to
be
say the token. We're going to take both of those things. I don't understand. These are two-way rules here.
Yeah, there should be two arguments basically. Each token event graph takes in two two-way rules, right, and produces multiple two-way rules.
Well, actually, it can produce one here. In this case, it's producing one two-way rule. It's taking each substitution lemma is taking two-way rules, which might be identical, right? Does that make sense?
Yeah. So you have to specify. If you just have one as an initial condition, you have to provide some multiplicity.
You have to make two copies of this, is what you're saying.
Yeah, a token event graph is not a function, it's a list of rules. So I'm just saying that the left-hand side of a rule is a list of two-way rules. Two-way rules.
Yes, I understand. So what are you saying? That the thing that is the event here takes two-way rules.
Right.
Okay, so it just takes two-way rules here, and #1 and #2 basically.
You just have to make it a rule, not a function, because the first argument of token event graph is list of rules.
Okay, fine. So let's say UV goes to values UV. Is that correct?
Right. Yeah. And no ampersand.
Okay, what on earth is going on here? So what is going on? Let's try running it a few more steps just to see if it does anything different.
Well, it can't make anything more.
Okay, let's try then the case where we have both this and the associativity lemma. Well, it's basically this. Okay, what is going on here?
Yeah.
And is there a question of canonicalizing and variable generation here? Isn't there a way in token event graph to let it use any multiplicity?
Yeah, it's just token multiplicity option.
Okay, so let's put that in there. Okay, so then here we've got these, and now we say token multiple. What do we do? Token multiplicity.
Arrow automatic.
That's more magnificent. Oh, for goodness sake. What on earth is happening there? Well, let's just try the more minimal case here first. Okay, what's that doing? Is this going to do any more?
I think it just repeats the same thing again and again.
Okay, so
maybe event deduplication. I'm gonna simplify it a little bit.
I'm sorry, what will it do that? Event
deduplication goes to true.
Okay, so that's showing. I'm very confused here. Why is this not showing two edges coming in here?
It gets duplicated. Maybe it's not a good deduplication. Just remove the duplicate edges. That's what it. Oh, what it does.
Event deduplication removes duplicate edges.
Yeah,
Okay.
That's weird. I know.
Not such a useful deduplication. Okay, but so let's make a more non-trivial version of this. So this is our vision of how mathematics actually works. That is, it is taking this collection of statements, it is combining them using substitution lemmas and producing other statements here, right?
Should we consider a less trivial case?
Well, I was going to, yeah.
Yeah, okay, good.
I was going to consider this case here. Is this going to do non-trivial things eventually, or is this the end?
Probably, yeah.
Nick,
It
it's
just
probably the
adds
end.
more.
Yeah.
It just
I
adds
don't
more
see
and
what
more.
else. I don't see what else it would make.
Okay, so how do we get a non-trivial example? Clearly, if we have variable generation, this is going to be a lot less trivial.
That's what I was going to say, right? That variable generation, obviously co-substitution.
We may not need co-substitution. I'm not yet convinced of that. So okay, so but we're not. Okay, the next issue here. All right, so I suspect this is going to be enough to generate non-trivial things. So now, this shows us explicitly how different statements combine together to make other statements, right? This here this is applying the axioms to statements, and this is self-applying to the axiom. So this is the analog of these things down here, but we're not explicitly showing up here how the events occur, right? So that edge there is just showing from this you can get that, and you can also get this. But then below we're showing that with explicit events, right? Okay, so now what axioms do we need to get something non-trivial out of this? And we have everything. Okay, so should we try our minimal this case here, A goes to X blank. Is that a useful self-applying rule or not? I think it's not.
No.
But a self-applying rule that would be useful is, oops, we don't really want that. We want this here. A self-applying rule that could be useful is X goes to YX. Do you agree?
Sure.
But now, how does that generate? Oh, wow.
Well, that's too
Four
much.
is, yeah, 4 is a little bit
down.
much. Maybe 2.
Every pair.
I don't want event multiplication. My gosh. Okay. What's this doing? So that's going into an event there. And one of the things it generates, but wait a minute, why is it not? It needs to uniquify, doesn't it? Otherwise it's nonsense.
Right.
Well,
Okay.
should we just uniquify that?
Yeah, we need to uniquify.
Yeah.
So that requires in this here, we need uniquify true. Now, can we canonicalize as well?
Yeah.
Whoa, man. Look at that.
Okay, so wait a minute. So now this is deriving.
I've never seen one that looked like that before. That's interesting.
Just a way with a way out.
No, I know, but I've never seen one with a layout like that before with the same setting.
Okay, so let's take this object here and just do, instead of the token event graph, let's make the, how do we make that as a multiwave graph?
I mean, how do you turn it?
This thing here will be able to do that, won't it? How do we get that? Instead of the token event graph, we want the multiwave graph for the same case. See what I'm saying?
Mm-hmm. Well, we've made multi-way graphs before, right, Nick?
It's kind of
I
the
know,
same.
but this is starting off from a particular initial condition.
Right.
How do we make, I think we need some kind of multi-way graph, or alternatively, we can just reduce the bipartite graph here. See what I'm saying? But where we reduce this, remove that, and just say it goes directly to these. Is that correct way to do it? Yeah, the issue here is, the reason that we can do that is because here, tokens and states are the same thing, basically. It's like the multi-way graph with numbers. We don't have to separate the notion of states, the state of mathematics, the whole state of mathematics, so to speak. Yeah,
We just use a two-way multi-replace graph list function, and it's going to do the same.
Wait. That has a cumulative stuff in it as well, doesn't it?
Well, token one graph also is cumulative.
No, it isn't.
Oh, it combines each tokens.
Oh my goodness.
You can combine any new token, any new pair of tokens. Basically, it can combine.
What is that?
That's just a big flat object. It's not interesting. It didn't manage to lay it out interestingly. Okay, what are you saying? What are you saying? So why are you saying that the token event graph is a cumulative?
Well, because you accumulate tokens and then you can combine them again.
Oh, I see. I see. So the point here that you're making is that's an important point. The token event graph is naturally accumulative. So, okay, so that means we probably need to worry about the accumulative case before we get to the token event graph case. But I see, actually, so accumulativity is not even very natural without a token event graph, I claim.
That's interesting.
And
Yeah, you just bunch all the tokens in one state.
right, not very natural without TEGs. Effectively, what one would do is collect every statement into a single state on which to apply the rule, on which to apply a rule, right, on which to apply a rule that picks up pairs of tokens, picks up pairs of statements.
That's interesting.
Right. So it really isn't very natural without token event graphs. And by the way,
If we ever made anything like that,
it won't be very nice because that's what we're talking about. That's what we're saying.
No, I understand. I'm just asking. I mean, have we ever in the past done anything like that?
Well, this is a question of how you do equivalencing in.
Right.
It starts to be interesting when you consider how you pick up those pairs.
Exactly. You have to know, but this is the question of what counts as a current state. I mean, this is, again, we can make branch hill graphs that represent current single states. That's a question of making the anti-chain that contains those statements that can be put into a single state. Right, because they need to be on an anti-chain. They need to be at a slice of a foliation. Otherwise, you have inconsistency of. But okay, let's keep going here because I think we're okay. So what we should be able to get from this. So the one thing we haven't done here, this would be from this we should be able to derive. So, e.g., the Boolean algebra case. I noticed a few comments on our live stream here, and Mark commenting about VR. You know, I got to tell a story. 1991, I was starting to think about doing sort of fundamental physics using networks and space made of networks and so on. And I thought, oh, VR is just around the corner. I will be able to visualize all of these lovely networks and so on in VR. Sure. And I'll be able to like pick them up with spider webs and like pieces of spider webs and so on, and see what's going on. And I'll see. I had this sort of vision of seeing these things more or less the same orange color of events and being able to see this network that represents space-time, so to speak, and see these areas that are very hot and keep on changing in other areas that are cold and don't change very much. Okay, that was 1991. Okay, ever since I've been waiting to make this realistic in VR. And like a year and a half ago, we built some VR capability for looking at least the hypergraphs built in the physics project. And I have this whole elaborate VR setup. I probably need to replace it now because it's probably already obsolete. I don't know. I mean, it was amusing, but not terribly. Unfortunately, we never managed to get the whole dynamic thing to work because doing dynamics of a graph and keeping the graph sort of pinned correctly as things are moving in it is a different problem. This sort of dynamic graph visualization is a different problem than static graph visualization. And I mean, the main thing I discovered is that, which I had discovered at different times over the last 30-something years, is that my predisposition towards motion sickness happens big time in VR. And people have told me, oh, once one has, sufficiently, once one has something where as one turns one's head, there's no delay in changing the imagery and so on, the motion sickness will go away. Hasn't yet for me, although it's gotten better, I think. So in addition to, so it hasn't been as useful as I had hoped for the last 30 years that it would be. Okay, anyway, back to Boolean algebra. So in this case, okay, so this is essentially our model for, this is our model for the generation of mathematics, basically, is what it comes down to. We start off with this collection of statements, in this particular case, just one statement, and then we start building things. So now let's go more ambitious, and let's go from this axiom.
Okay, yeah.
We're going to build Boolean algebra. Because we know we can. I mean, that axiom alone should be able to make Boolean algebra from this kind of setup. So I believe what we have to do here, and this is going to now generate variables, right? So, but then Uniquify. This is pretty crazy, actually, but it should work. Oh,
yeah, but yeah, it's going to be very explosive too, because there are many places that you can insert it.
Okay, well, let's go. How do we not label the things? Can we get rid of the labels? We just say vertex labels goes to false.
Token labeling goes to false.
Goes to false or none?
I think it doesn't matter.
Okay. Oh dear. Oh dear.
Yeah, it's exponential, right?
Perhaps worse. Okay, let's go rule-logical and let's just start enumerating axiom systems.
Okay.
So, I mean, what should happen here?
Oh, yeah.
This is a bad, so it's going to do something. Let's see what it does. Ta-da. Oh, look, that's pretty jolly. Come on, resize.
Okay, well, that's interesting.
Does it have tooltips? No, it doesn't. That is quite something. I mean, what that is, wow, that's basically the intrinsic generation. I mean, this will eventually generate all true statements of Boolean algebra, I think. I think it's enough to use substitution lemmas, isn't it? That's a question we don't actually know the answer to.
This is a big question still.
It depends on your rule. Maybe this one is actually enough because it has just one variable on one side.
You mean because it's variable generating, substitution will suffice?
Oh, Nick is saying because it's a single variable on one side. I think you're right, Nick, because I think then it doesn't need
but isn't that what I just said?
No, because this is pure substitution is enough because there is a single variable on one side.
But isn't that what a variable generating rule is?
No, No, because it could have just unequal numbers of variables on each side.
It means basically it's the most general pattern that you can have. You just can match this variable with whatever sub-pattern.
Right.
Your expression.
Now, so in more generality, we probably need co-substitution in order to get everything.
Right.
I bet that's right. I bet that's right, because it's effectively, yeah, okay. All right. So in this picture, well, actually, let's go ahead and 420. Okay, so this is rather fun. I mean, let's get rid of all the events here. We want the vertex list. We want the cases of that, comma, blank two-way rule. Okay, these should be true statements of Boolean algebra. Should we check that they actually are?
Please. Yeah.
We actually did check it at some point.
We
Well,
did.
these are,
Yeah, we did. We just tried all combinations of true and false for variables, and we got everything true.
for this case, for the case where we just went 2 levels?
Yeah, it was something similar. Maybe I can even fish out the code for that somewhere.
Yeah, well, so how do we get rid of the blanks here? We just say pattern goes to whatever, right? Or we could just do Boolean table. What's that?
Well, blank pattern goes to first of that pattern. That's going to replace it with this symbol. Maybe P blank pattern goes to first of P. Something like that.
Okay. Okay, so now the question of whether these are true statements of Boolean algebra depends on the interpretation of dot.
Yeah, that's an AND.
I know, but
yeah.
So if we take this and we say, oh yeah, this is going to be an amusing test. So we take this and we say center dot goes to NAND and two-way rule goes to equal. Okay, and now we say, let's just take random sample of 10 of these. Oh my God, what a complicated mess. Okay, so now let's say Boolean minimize of these. Pathetic. Okay, so maybe we try Boolean table. How do we do Boolean table on these? Does Boolean table automatically deal with arbitrary numbers of variables?
I don't know that.
You have your model generator, right? Your model tester.
What model test? Like for find it models?
Yes. Because then for this, what we should be doing is for each of these. Well, okay, so let's just take the first of this. What the heck is that? How can it be that? I don't understand. It's got all these variables, A, B, C through J.
Maybe it's not smart enough to extract those variables. Something.
Not a good sign. Okay, how come there's anything false in there? How can there be something false there? Let's try for the original axiom.
I can like send you a code that we tried it last time.
Please.
Just part of it.
What is this doing?
So first, you're just generating all combinations for 7 variables, assuming that you have 7 variables, right? And then it just given a graph, like you can just give it a graph above.
The heck is that?
Well, we have a G there. You see, you just replace this G with some graph.
What kind of a graph? Oh, vertex list.
Well,
Okay, so this is, so that's our %424.
yeah.
But why is there 7 variables? We don't know how many variables they're going to be.
Oh, we just like how we did it.
No, I understand. I mean, this could also be a tautology queue, right? And it says false, which I don't like. I don't understand that. Okay, let's take the original axiom.
Maybe it's something to do with like Uniquifying and canonicalization process.
Well, I think we're getting the wrong answer. It's basically the problem. I mean, I'm pretty sure we're getting the wrong answer somehow. Okay, well, that's encouraging. Okay, so we have to figure out why we're getting the wrong answer. And yes, I agree. It might be very well be to do with but conceptually, this is the right thing here. And so conceptually, what should happen here is that a proof from find equational proof should be a path through this graph. Correct?
Yeah, I see. Yeah.
Okay, so but it's a very good point that this is naturally accumulative. All right, so I think what we have to do, the next step, which we are not going to do right now, is to look sort of rulologically at simple axiom systems. First, we have to debug this and find out why this is not working correctly.
Yeah. Okay.
And then okay, it's looking to me like co-substitution is going to end up being an important appendix-like thing, not a main event thing. We're not going to need it. So, okay, Nick, you were just for a few minutes. Let's talk about the MetaMath thing that I think you said you had.
Well, what I had is just a convenient way to work with proofs and extract some kind of graphs for Metamath proof.
Right. I feel bad because I know it's the very end of your wake cycle. So, but we are going to wrap up soon here. Okay. So, do you want to share something, or do you want to? How should we do this, or is there a file?
No, yeah, just a file of Metamath proof.
Okay.
In
Okay. By the way,
same folder.
William asks an interesting question on our live stream about self-replication. Is there an analog of self-replication in mathematics?
Yeah, I mean, there's something.
What's that?
Recursion.
Well, no, there's something else, which I've just been calling it propagation, which is you have to have, and this goes back to whether or not something is observable, right? It has to give some sort of, it has to propagate some sort of behavior that can persist in its entailment cone in metamathematical space.
Yeah, the question of self-replication is different from the question of persistence. I do tend to think that with all of the things we now know, we may be able to get a better abstract definition of life that includes this notion of, there is this notion of persistence and integrity about life that is a little different from, in other words, a living system has the feature that, if you have a rock, you say, is it the same rock? Well, you chip pieces off it and things happen, and maybe it's the same rock or maybe it's not, but you don't have a very clear definition. Is it the same organism? Most of the time, absent, random cell division-y, protozoa type things, you pretty much know that is, okay, there are weird corner cases, but that is a person, that's another person.
Yes.
In a way that you don't so clearly with, it's a single integrated thing. And obviously it gets more obscure when you get into, well, it doesn't get that obscure. Even single-celled organisms, it's pretty clear that it's one organism and not another. So this notion of identity, actually, I had thought about this idea that another criterion of something related to consciousness is the belief that there are entities like you. In other words, one thing is that there are, one thing is the concept that there's a continuing entity that is you, that is persistence, so to speak. And the other feature of sort of human-like consciousness is the very anti-Descartian or something kind of idea that there really are other entities just like you, which is not a self-evident thing. If you, from inside yourself, you can't guarantee that, but that can be your view of the world in just the same way as your view of the world is, even though you're made from different atoms of space at different moments in time, it is still the case that you imagine that you're the same you at a later moment in time, even though you're made of different atoms of space.
But in this case, you're not just referring to the observer, how the observer feels about itself, but to other potential observers.
Yes, that there are other observers.
Well,
in other words,
well, the species wouldn't survive otherwise, right? You have to have what's called conspecific recognition. You have to be able to recognize members of your own species. Otherwise, you'd have a terribly difficult time maintaining a population. You wouldn't be able to recreate the population or grow the population.
Indeed, like that old giant tortoise that I met when I was a kid that was the last of its species. Anyway, it was at London Zoo.
It sounds like a sad story. Yes.
Okay. In any case, let's metamath thing, and then we've got to wrap up.
Well, who would have thought that metamathematics inspired by physics would afford insights regarding biology?
Well, but yes,
so
these things are very related, and that's why that's why this whole multi-computation paradigm thing is fairly general. Luis is asking, is there a relationship between hypergraphs and the P versus NP problem? Yes, the answer is yes. But that will get us so far off track here that we're not going to discuss it. And I can recommend that there's a discussion of that at the end of the piece that I wrote about multi-way Turing machines.
Yeah.
No, actually, Turing machines and Rullial space. There's okay. Let's look at your next thing, and then where was that now? Metamath.
Not ready. The positive function.
Oh, okay. What is it called?
Metamath proof. The second one.
At the top, yeah.
Okay, so let's run this and then I assume it has some examples because it was huge, so it must have. What on earth is this? Oh my gosh. Well,
yeah, so there's like two Metamath files. You either want to pick set mm or the one from Boolean axioms.
let's do the one with Boolean axioms because that's the thing we were just looking at.
Right.
Yeah, so at the top I have it like iconized, I think. Importing it.
This one here.
Yeah, the iconized one.
We got to 24, didn't we? Yeah. Okay, what is this now? So now, what is this going to do?
So now you can like Metamath proof of that and ask some properties of any proof from that file, like tree, graph, and stuff.
What's this random choice of theorems?
You
What's
can
theorem?
you can just check the list of theorems in that file.
Okay. So those are various random lemmas.
Yeah. So like try L1, for example, or L2, L3.
Okay, how do I do that? Just how do I?
Instead of well, the first argument, instead of random choice, you just pick a name for a theorem. And get like a proof tree.
What is
where
it?
Well, basically each node or leaf is just a variable for an axiom when you can, that does substitution basically. So all the leaves of each node is kind of replacing a variable inside the expression. So you can evaluate this tree and just produce a sequence of characters that's gonna correspond to the statement of your theorem. So the fact that you prove
where's
the theorem,
the input? Are the leaves the input?
Yeah.
Okay, so can we think of this as a token event graph or not? What's the relationship between this and a token event graph?
That would be just like one token, I guess, because it's just one token. It's just one expression. It's just encoded.
But this is the proof.
Yeah, but
this isn't. Yeah, go ahead. This is not just the expression, because it's not just in the analogy of what we're doing, wherever it was in here. right? Every node here is a theorem. Its proof.
Well, the analogy would be if you like reverse this tree, like bottom to top, then you like each node's gonna take an input, like two variables or more than two, and produce well something. Then you just take this input and feed it into another node. So each node is an event.
I'm fairly confused. Okay, so is there a simpler case of this? Could we get, or is it too difficult to encode, the same thing that we were? Oh no, okay, because these are by hand proofs that have been done.
Yeah.
And this is a representation of the by hand proofs.
Right.
So the question is, okay, and what is the relationship between these proofs and the find equational proof proofs?
Well, if you make like expanded tree, expanded graph, I think that's going to be more clear because it will show an input. Basically, it combines all the equal leaves there into one, and also highlights the input.
Okay, so wait a minute. What's the input and what's the output?
The top one is the name of the theorem, and red nodes are your input. So there's 4 variables.
What do you mean by input? I mean, so in find equational proof, we would be. Go ahead.
Well, it means that lemma contains 4 variables here, and you can substitute those variables with something else, like different Boolean expressions in this case. So it's like
but
having
why is
4
this a
patterns.
proof? Is this a proof? Is this graph representing a proof?
It's a proof in the sense that when you evaluate it, like if you just execute those 3 above, it will produce an exact statement of your proof, just a sequence of characters. Because each event or node that doing some substitution. And if you just do the substitution for like fold this tree, doing all the substitution, it will just result in one sequence of characters. And if it's equals to the exact statement that you want to prove, then this is a valid proof.
Okay, I need to understand this better. But I mean, basically what we think we'll be able to do with this is if the proof we're looking at is the Pythagorean theorem, for example, we will have a particular proof of the Pythagorean theorem here based on a particular underlying axiom system. Is that correct? From set theory.
Right.
Okay, so we actually don't know from that. We know nothing about the halo of the Pythagorean theorem. We just know a specific tower, which is the Pythagorean theorem, and lean might give us another specific tower.
Right.
Yeah.
Well, we can kind of grow some branches.
How?
Just grow this cloud. Well, we can use all the lemmas that this theorem used and maybe attach other proofs to it.
Okay,
So
but that's using automated theorem proving-ish type techniques.
Right.
No, not automatic. I mean, just if you have 2 proofs that have one lemma in common, you can just connect those. So they kind of.
I have to disappear to go to something different here, but this has been very useful. We've got a little bit of debugging, I think, to do here. Could we, if you are able to debug this, that would be very helpful. And then, James, if you're around later, if you want to do some ruleology of trying to find a simpler version of this, that will be helpful.
Great. Yeah. And I mean, we have something in the calendar for later today as well.
I know that, but that's like 7 hours from now.
No, I know. So yeah, between now and then.
Right.
Boolean ruleology sounds like fun.
Right.
Yeah.
And I will probably write some things based on what we have been doing, the examples we have here, and that will generate some more needs. But I think we're getting a pretty decent idea of how this is coming together, and we're going to need. Yeah. Okay. This is fascinating stuff. All right. I have to
Indeed.
go.
Indeed.
Thanks to folks on our live stream, and I think we should at some point. I have on my list working on the origin of life and definition of life, and we probably should do something on that since we are all living systems. Seems like an important area.
Sure, and it was. I mean, this was something you said we would do when you wrote the multi-computation post. Indeed.
All right. Okay. Thanks to folks on live stream.
Yeah. Thanks, everyone.
Okay.